Welcome to the Explainer. Today, we're going to get into something that's part science, part art, predicting the future. We're breaking down an absolutely fantastic presentation prepared by Dr. Nima Mahadian, and we're going to figure out how we can build models to see what's coming next, even when the world throws a little bit of chaos and randomness into the mix.
So let's start with the big question, right? Think about it. Almost everything in life, from the stock market to the weather, has some randomness baked into it. It's unpredictable. So how in the world do we build a reliable crystal ball when the universe is constantly rolling the dice? That's the core puzzle we are going to solve together today. All right, here's the game plan. First, we'll set up the puzzle itself. Then, we'll talk about the huge difference between simulating and predicting. After that, we get to the fun part, actually building the best possible predictor. Then, we'll uncover a secret hidden in our mistakes, find a really surprising connection between two different fields, and finally, bring it all home to see how we can turn messy data into real foresight. Let's dive in.
Okay, first up, the prediction puzzle. To even begin to predict anything, we need to agree on the rules of the game. We need a fundamental equation that describes how pretty much any system works. Okay, now don't let the math on this slide scare you, because the idea behind it is actually pretty simple. This equation is basically our map of reality. That y of t on the left, that's just what we see, what we measure, the temperature, a stock price, whatever. The equation says that what we see is made of two main ingredients. The first part, with the g and the u, is the predictable part. Think of u as you turning the steering wheel in a car. You know you did it. And g is like the car's physics. It's the rule book that says when the wheel turns this much, the car goes that way. But then there's the second part, with the h and the e. That's the randomness. EFT is pure, unpredictable static, like a little bump in the road you couldn't see. So all this equation is really saying is that reality is a mix of predictable cause and effect and a little bit of random chaos. All right, so now that we have this model, what can we actually do with it? Well, it turns out we can do two really powerful but very different things with it. We can ask what if, or we can ask what's next, and telling them apart is absolutely crucial. Think of it like this. Simulation, on the left, is like playing a video game on God mode. You know all the rules, you control all the variables. A flight simulator is a perfect example. You can say, what if I fly into a hurricane? And see what happens, because you control the plane and the hurricane. But prediction, oh, that's a whole different ballgame. That's real life. You don't know what the future randomness will be. You're not asking what ifs. You're asking, based on everything I've seen so far, what is actually going to happen next? It's forecasting, not just fantasizing. Yeah, this image really nails it. The model we build is this incredible bridge. If you look backwards over your shoulder, it helps you make sense of all the data you've collected. But when you turn around and look forward, the bridge forks into two paths. One path is simulation, exploring a whole multiverse of possible what-ifs. The other path is prediction, trying to chart a course into the one single future that is actually going to happen. Okay, this is where things get really interesting. We're done with what if, we want to know what's next. So how do we make the best possible guess about the future? I'm not talking about a gut feeling, I mean the best, mathematically proven guess that you can possibly make. All right, a little more math, but stick with me because what's happening here is super clever. Imagine we're standing at time t minus 1, right now, and we want to predict what happens at the very next moment, time t. All this equation does is take our original model and just rearrange the furniture. It brilliantly sorts everything into two buckets. Inside that big bracket, you have everything that can be calculated from the past, all the inputs and outputs we've already seen. And then, all by itself on the end, is E of t. That's the ghost in the machine. The one piece of pure random fuzz from the future that is impossible to know. We've literally separated what's knowable from what's unknowable. And now for the magic trick. To get our best guess, we ask, what's the most likely value or the average value of this whole thing? Well, the best guess for the stuff we already know is just the stuff we already know. That doesn't change. But what about our best guess for that future random noise, ET? Think about it. By definition, it's completely random. It's just as likely to be positive as it is to be negative. So on average, what is it? It's 0. So our best guess for the unknowable part is simply 0. And just like that, poof, it vanishes from our equation. And what are we left with when the smoke clears? This. This is our optimal predictor.
Our best guess, which we call y hat, that's what the little hat means, is simply all that stuff we calculated from the past. We've created a perfect filter that takes all of history, processes it through our understanding of the system, and gives us the single best possible guess for what's about to happen next. Now let's be real, our prediction is never going to be 100% perfect. There's always going to be a little gap between our guess, our y hat, and what actually happens, y. We call that gap the prediction error. But here's the really cool part. That error isn't just a failure, it's actually hiding a huge secret. And here it is, the big reveal. That error, the difference between our guess and reality, it's not just some random mistake. If we've built our model correctly, that error is exactly equal to E of t, the pure, unknowable randomness that we decided to ignore a minute ago. Let me say that again, because it's so important. If your model is perfect, the only reason your prediction is wrong is because of the fundamental randomness of the universe. Your error is that randomness. This idea is a total game changer. Why? Because it gives us the ultimate test for how good our model is. If your string of errors looks like pure TV static, completely random and unpredictable, then congratulations, you've done it. You've built an amazing model. But if you look at your errors and you see a pattern, if you can predict your own mistakes, well, that pattern is a clue. It means your model has a blind spot. Your mistake becomes your roadmap to a better answer. Okay, get ready for a plot twist. We're going to take a little detour into a totally different world, the world of control theory, and we're going to find a connection that is just mind-blowing. So over in control theory, they're doing something that sounds different but is weirdly similar. They might have a robot arm, and they have a perfect little computer model of how that arm should move. But in the real world, you get friction, vibrations, stuff happens. They call all that messy reality a disturbance. To deal with it, they build a tool called an observer. Think of it like a little supervisor that's constantly comparing the perfect model to the real robot, and every time it sees a difference, an error, it uses that error to nudge its internal estimate back on track. And here is the grand finale. This is just so cool. When you take the math for our optimal predictor and you put it right next to the math for their observer, they are literally the same thing. The exact same equation, just wearing a different costume. Our predictor is a perfectly tuned observer. It's incredible. Two completely different fields working on different problems, basically tunneled through a mountain of mathematics from opposite sides and met right in the middle. It shows you just how deep and fundamental this idea really is. Wow. Okay, so we have been on a pretty deep journey through the theory. Let's pull back up to 30,000 feet for a second. What does all this machinery actually let us do? How do we get from all these equations to actually, predicting something useful? This diagram lays out the whole process perfectly. You start at stage 1 with messy, noisy, real-world data. Then you move to stage 2. You build a model and you make predictions. But here's the crucial loop. You analyze the error. You ask, is it random or is there a pattern? If you find a pattern, you use that new knowledge to go back and improve your model. And you just keep going around that loop, refining and improving until the error is as random as it can be. Only then do you reach stage 3, a validated model that gives you real, confident foresight. So let's boil this all down. What are the big ideas to take away with you? Number 1, prediction is all about drawing a clean line between what you can know and what is truly random. Number 2, for a great model, the prediction error isn't a mistake. It is that pure, unknowable randomness. 3, and this is a big one, this makes your error your most powerful tool. It's not a failure, it's a guide. And 4, these ideas are so fundamental that they show up in different fields of science and engineering, proving they're a deep truth about how the world works. And that leaves us with one last big thought to chew on. We've just seen that the key to building a perfect model is to obsessively study its imperfections, its errors. So, what if that's true for more than just models? If being wrong in just the right way is the key to scientific progress, what other mistakes in our own thinking or in our lives might be holding the secret signal to a much deeper understanding? Maybe getting things right isn't about avoiding errors at all. Maybe it's about learning how to pay much, much closer attention to them.